Everybody, I'm David Abrahams. I'm the director of the Isaac Newton Institute for Mathematical Sciences, and it's a great pleasure to welcome you all here to our inaugural Kirk Distinguished Fellow Lecture, and you're the very first, so thank you very much. It's Claudia Sagastizabal from Unicamp in Brazil, who's here visiting on our Massive Energy Systems program. So it's a great pleasure to have you here, and we look forward to hearing your talk. If you'll allow me just to say a word about the Kirk Distinguished Fellowship program. This is something we've just created, as I say, thanks very much to the benefaction of our chair of our management committee, Ewan Kirk, Dr. Ewan Kirk, who's a generous benefactor of the Institute, and he's done a lot for mathematics here next door as well as here. We have 4 other Kirk Distinguished Visiting Fellows due to, well, 2 are going to be here giving lectures very soon on the other 2 programs we have running. That's Irene Fonseca and Svetlana May-Boroda. And later in the year we've got 2 further programs, and the speakers for those will be Donatella Marini and Leslie Ward. We'll advertise those, of course. We have a great program, and Ewan Kirk, our chair of management committee, was very keen on helping us with our aim to redress the balance in the mathematical sciences community. So the INI recognises very clearly its responsibility for broadening the reach, widening participation, and creating opportunities for everyone who wants to study mathematics and to represent our community to do so. So I should say a lot of the efforts of this have gone down to my deputy director, Christy Marr, who unfortunately can't be here today, but she's been working tirelessly to work up the gender balance within all of our programs. And she's done a magnificent job. In just a few years we've raised our average numbers of female participants in all of our programs from around 13-14% to nearer 23%. So we have some way to go to get gender parity, but still we've improved dramatically. And that's mostly at the early career and mid-career level. So where we still are very short is the representation of the very senior female figures in our community who can be role models for everybody else coming through. And so thanks to Ewan Kirk's generosity, we can now put our female speakers up at the very highest level. And our speakers on the Kirk Distinguished Fellowship Program are at equal standing and have equal terms to our other fellowship program, the Rothschild Fellowship Program. However, we recognise that we don't want to ghettoise the females for being in one position and the males in the other, so we're waiting to see which program will have 2 female speakers on our Rothschild and Kirk Fellows, and that will happen very soon. Anyway, that's enough from me. I would just like to say thank you for coming along, and I'd like to pass on to Andy, who's going to say a little bit about our speakers. So thank you very much and welcome.
Thank you, David. Well, welcome to the Kirk Fellowship Lecture, the inaugural one, and we're very fortunate to have Professor Claudia Sagastizabal from Brazil to present this lecture. Claudia is originally from Argentina, not Brazil, and she did her PhD in Paris with Claude Marechal, and has worked a lot in energy optimization, EDF, but also in Brazil with the energy organizations there and in other countries as well. And her main research areas in decomposition methods for solving very large-scale optimization problems which arise in these energy applications, especially in EDF and in Brazil, and she's a world leader at this, and I'm very much looking forward to hearing what she has to say in her 3 character archetypes in energy optimization.
Okay, thank you, Andy. Thank you for this invitation. Thank you for being here. It's nice to be pinpointed for this distinguished lecture, but what is even nicer is that to have the opportunity of being for a long period in this exciting place that provides such an stimulating environment for research. This is something that you are doing very well, so it's something that I appreciate, especially the opportunity of exchanging with colleagues from other areas. So expanding mathematics broad. And part of my message today is that there is not mathematics for women, mathematics for men, mathematics for third world. There is good mathematics and bad mathematics, and there is no pure and applied, in my opinion. There is a big area where we all communicate, and I see mathematics as a language, which, like English, I speak with some accent, but I'm pretty sure that the message you will understand. And this is what is great about mathematics, it's universal. Okay, so I will start my talk asking questions. 3 questions that may not be related and that I will use as a guideline when answering them to, well, like a skeleton of the talk. So first, what is the fastest method that you know to solve a nonlinear system of equations? You all have in mind, I suppose, some name, right? Just not unrelated to the institute. Okay, so and that's why I chose to start with this question. My second question is, how much are you paying for electricity? You will have to wait for the answer to this one. And the third one is if you ever heard of the proximal point mapping. So those 3 will be my leading questions in this, I don't know, this road that will we do together during this hour. Okay, the answer to the first question, yes, it is, we all know it's Newton's method that is the fastest to solve nonlinear systems of equations. And how is it that the Newton method starts? Suppose you have a nonlinear operator G, capital G, and then you want to find x star that is a root of this system, it's seriously system. Since it is difficult, then we define a sequence of iterates xk, and asymptotically we will converge to this x star that we are aiming at. And then, since it is difficult to solve the nonlinear system of equation, what we will do, we'll linearize. We'll make a linear model of the nonlinear system. It will be a Taylor expansion of first order, centered at the current iterate. So it's the operator at the point plus this here is the Jacobian, G prime. And then, instead of solving the nonlinear systems, D will be the solution of a linear system now. And we will provide the step or the direction that added to the current iterate will give us the next xk plus 1, and the process will continue. So we all know this method. It has fast convergence when we start sufficiently close to our solution, x star. All those are local methods. When we speak about speed, everything is local. It's we were starting in some ball near the solution, and then graphically we have this blue curve is the very simple nonlinear mapping 1 plus x cubed divided by 3 has one solution here, 1 0 here, minus 0.87, something like this, and then instead of finding the 0 of the blue curve, at each iterate, we define a linearization and find the 0 of the linearization. And the process continues so on until we converge. Of course, depending on the situation, we may diverge, because Newton method is also very fast to diverge, but here you are in the good situation. Good, so that's a method, and it converges fast. Here is a graphical illustration on what I mean by fast. We have here on the left iterations starting for this very simple mapping, starting from a point equal to 2, and then the successive iterations until we find the eighth one, the root. In color here I showed the fast convergence I'm speaking for. You see there is this semantic of color here. Here is represented with numbers, how many significant digits we get at each iteration. And when we speak of fast, in fact, we mean accurate. Newton method gives us digits of iterations that we cannot grasp otherwise. And you can see, well, once we enter the region of convergence, you should say, we start doubling the number of accurate of digits of precision, and this is what we appreciate, what we like about Newton method. So fast is quick and dirty for, in fact, meaning accurate. This is, it may be very well be that one iteration entails more computational work than one with another method, but it will give us big progress. And this is the characteristic of this type of methods. Okay, so this is the Newton method for solving a linear system of equations, but we are talking about optimization. So for optimization, we can think that finding the zero of the operator, of the nonlinear operator, is the optimality condition for minimizing an objective function f. So everywhere where we have g, now we have gradient of f. And hence here where we have the Jacobian, we will have the Hessian of the function. So this is the Newton method for optimization. And we see here that the work that we have to do at each iteration is still solving a linear system, well, and computing second-order derivatives that may be complicated, or well, it's we have to fill a whole matrix with numbers. Well, half of it it's symmetric. Contrary contrary to the fact here we have only a vector. So here we have n numbers, and we will have here we have to compute n times n plus 1 divided by 2 numbers. It's much more heavy if n is large. Okay, if we remember that in fact we are minimizing a function, not only finding a zero of a nonlinear system, we see that when we solve this, when we find the next iterate in the Newton method, in fact what we are doing is approximating up to second order, the second order Taylor expansion here about xk of the function, and this gives us a quadratic polynomial, and we are, in fact, if we write the optimality conditions for this system, for this problem, we have the Newton direction. So, in fact, we are replacing our function that is difficult with a model that has information of second order. And this is why the method is fast. It has information higher than first order. So if we now we want to do our illustration on the very simple function, but now sort of as a function that we want to minimize, not that a gradient we want to find the zero of. We have the blue line, and then at each iterate we will be approximating our curve blue that we don't know with the model that is a quadratic. I'm sorry, by the way, see that this is a polynomial of degree 4, right? That we want to minimize, and we are replacing it by a model, a quadratic model that along iterations, will be varying because we are centering the polynomial at different xk. One thing that is important to realize here is this. What is the interest of putting a lot of effort in computing the Hessian matrix? After all, we are, let me go back a little bit here, we are making a model about this point, but why would we kill ourselves computing this Hessian that is complicated if when we are far from the optimum, right? Maybe we can avoid performing so many calculations, and well, this is the idea behind the quasi-Newton family of methods, where we replace the Hessian matrix by a matrix that will be updated also along the iterative process, and that we will compute this matrix using gradient information without having to compute second-order derivatives, and also in a manner that makes the linear system easy to solve. Maybe preserving some sparsity pattern or ensuring that we keep things positive definite, things like this. Okay, so this is called the quasi-Newton matrix, and well, here I just wrote the system that we are solving. Okay, just well, to see that the matrix is replacing the Hessian of the function at xk that we don't want to compute because it's too heavy. So what about the convergence of this type of methods? Here we have then our original function, in red the Newton model, quadratic model, and in magenta the quasi-Newton model. So what we need to have convergence for the quasi-Newton iterations is we don't need to ensure that at each xk we are approximating the Hessian with our matrix. What we need is that eventually, as we converge to the optimum, the Hessian is approximated, and not along in the whole space, but only along the directions that are being generated by the method. Okay? It's not everywhere, it's only where we are looking at our function, let's say. And this is the Denis-Moreau condition that characterizes superlinear convergence for this type of methods. So what is important to remember here is that the true Hessian, the second order information, needs to be estimated only along some directions, not in the whole space. Good. So now the semantic of colors, on the right Newton, on the left quasi-Newton, and you still see that we gain quite a lot of digits per iteration. Of course, a little bit less than with the Newton, pure Newton, because we're using less information. It's a little bit more inaccurate, since it is an approximation of the Hessian. And, but still is quite good, and still we get a lot of digits. So it's still accurate, which is what we are looking to, what we want. Okay, so first order methods. What if we want to do something using only gradient information, then without computing approximations to the Hessian, which amounts to making some step in minus the direction of the gradient of the function with some step size chosen sufficiently well, let's say. If we do, it is very easy. Now we don't have to solve a linear system. It's just a calculation. What is that we can hope to get? Well, here is a drawing for the same function. Here are the gradient values and along iterations. After 100 iterations, you see this is we stay near 0.5, then boom. There is we don't advance, we don't advance, we don't advance. We get very similar values along many iterations, and all of a sudden we reduce the function that we want, the value that we want to 0. And so on and so on. But so this is typical of first order methods. First order methods, they are fast. So those calculations are done very fast. But after 100 of those fast iterations, we got this minimized at this point when we are looking for this one. So we have, I don't know, one digit, one digit of precision. And if we compare here then graphically the x values, then now, so we started from 2, remember, and then we're going to minus 0.80 something. In red, we see how slow, so I cut it in 100 because, well, we never reach the precision that we want with the first order method, while the Newton, I just amused myself, no, I didn't stop, make the stopping test, and then, well, it kept on computing the same. After iteration number 9, that is when it arrived to where it had to arrive. And regarding the values that are supposed to be 0, with the gradient methods we are in this value, 0.09, and with Newton methods we have already in the 9th 16 digits, or well, 15, something like this. So this is important to keep in mind, because of course for some applications methods that are fast and give an approximate response are very useful. For others it is not the case, and this is the case we are interested here, so where we want accuracy. Okay, so what are the takeaways messages from this first part? Newton-like methods are fast, but fast means accurate, number of digits, and this is important. And accuracy, how did we reach it? We reached it by using a model of the function that had some curvature, more than first order information. We put this curvature given by the quasi-Newton matrix MK. And this matrix does not need to approximate the Hessian in the whole space. We know from quasi-Newton convergence theory that we only need to do things right along the directions of the iterates we are generating. So in a region or a subspace. That is for functions that have sufficient smoothness and have an invertible Hessian at x star. Okay? Good. What happens when we move to the non-smooth world? And let me tell you, it was difficult to find a map, a globe with South America here. It's not easy. Okay. So, because the applications we have in mind are always involving some degree of non-smoothness. And this is related to the second question. Our second question refers to electricity prices. And if you are a person in the street and you think, how do we give a value to the electricity? You could say, well, it is how much it was spent to generate it. But when we press the button and turn on the light, we don't know if the light comes from a wind farm, from hydropower plant, from nuclear, from burning some fossil fuel. And all those technologies have a different cost, right? And if we pay for the cost of the more expensive, then, those will be making a lot of money. So there has to be, the price of electricity has to be defined in a manner that is technologic independent, something like this, let's think, okay? Or that takes into account all the technologies involved to make the process, because we don't know from where it comes when we use it, right? Here on the right, there is just a diagram of the fact that hydropower plants are usually connected and in cascade along a basin, a river, and then when the one uphill produces electricity, it releases water and then gives the combustible to the one that is downhill to be able to generate electricity too, and so on, right? And sometimes when it is convenient, it can be also be useful to pump up some water so that it is waiting there and it is ready to be available to generate electricity when there is peak demand, okay? So that's a way we have of storing energy, by the way. It's the water. Good. So how do we price electricity? What it seems reasonable, or well, if not, it's the way we will do it. It's to think what is the value for the whole system, for the system as a whole, if we all of a sudden we have to produce one more unit of energy. How does this impact in the whole system, in the generation of the whole system? So all those power plants are interconnected by electricity lines and so on, so it is rather complicated to describe mathematically these kind of relations, but we need to take into account the whole system. Okay, so this is called the fact of assessing the value or the impact that generating one additional unit of energy it has for the whole system is called the marginal cost. And since it is related to the electricity, to the price of electricity, which has a tremendous impact in the society, an economic impact in the society, we want this calculation to be done with accuracy, okay? So all this that I said before, it was because we want to compute with many digits these price signals, or this marginal cost. Well, and speed is also preferable if we don't have to spend the whole day making the calculation. So how is it that we compute the marginal cost? And here is the answer is given by another character, is Joseph Louis Lagrange, who was an Italian who had his career in Germany and then in France. He was professor at École Polytechnique, and this is a copy of one of his notes he was teaching with. And what is cool is that you can still buy those books in Paris. Near Pantheon, there is an editorial that publishes these old books of the masters, mathematics. You can buy Galois, Writings, or Poincaré. I suppose here somewhere there must be also some bookshop like this. They are still making the editions. It's difficult to understand, but well, anyway, they are there. So what is the price of electricity? No, because it's written, it's difficult, the calligraphy. So suppose we have two power plants, thermal on the left, on the right, and hydro on the left. This is a very nice dam in Brazil, by the way, all those pictures are from there. And then to express the way each technology produces electricity, we will say the hydro generation belongs to the hydro set GH, and similarly for the thermal, right? We are not spending more time in describing this. And then each generating each type of power has a cost. Clearly, it is more expensive to burn a fuel than just to release water. And what couples the generation of those two power plants is the fact that the sum of all the power that they produce needs to satisfy the demand. Okay. What about wind? Well, if there was wind, what we would do, since we cannot store it, it is a non-storable renewable, then we will subtract it directly from the demand, and we will satisfy with the other generation the demand that is left, the net need from the wind. I will not give any more details here. Okay, it's not it will not change the ideas that I want to transmit. So we have the two. Our power system is simple. We have not even time steps. It's only one moment. We have two sources of energy. We have the demand that couples the generation of those sources. So if we want to operate this system economically, we will try to solve the optimization problem that is up here. Good. Okay. So if we want to define the marginal cost, we need to know how much this total cost changes when we increase the demand in 1 unit. This is what we were saying is the marginal cost. Okay, so mathematically, so here we have our problem where we have changed our demand, increasing it in 1 unit, a perturbation U, and I have put an if because we don't know if we will be able to attend all this demand, so it's no longer a mean. And we consider the results of the value of this, the optimal value of this problem as a function of the perturbation. And this is the perturbation function that is the key to price electricity. If we want to know what is the cost increase if demand increases in 1 unit, what we have to compute is the directional derivative of this function. So, where do we have to compute the directional derivative? When the perturbation is equal to 0, because we go to our original problem that we started with. Is the P of 0 is the optimal value of our problem. Good. And what is the directional derivative of this perturbation function? Here is given by Lagrange. That's why we were talking about Lagrange. Is the Lagrange multiplier associated with this constraint? That gives the directional derivative. And so it gives the margin, the rate of change of the cost for the whole system with respect to variations in the demand. So what are the Lagrange multipliers? So here I just rewrote our original problem in a more convenient way with the constraint, so that we relax this constraint with a multiplier that is called x, here the dual variable. So the Lagrangian depends on primal and dual variables, and it is the objective function plus the inner product between the constraint and this multiplier. So we are penalizing in the objective, we are penalizing this constraint. And it's a constraint that was coupling the generation of the whole system, so of the two systems. So if we look at it, the fact that now, so it's the same so except with colors, that now so we move to here the constraint. So now if we consider the problem, the dual problem that is associated then with the Lagrangian, that consists in maximizing the dual function. The dual function is the minimum of the Lagrangian in the primal variable, and then it is then this doesn't depend on G, so it's a fixed term. And then we have two terms one per technology. And this is very important and is very useful, and this is why often we resort to some sort of Lagrangian relaxation in applications. And this is the source of the composition analysis that Andy was commenting. Okay, the dual function that we want to maximize, and so instead of solving the primal problem, we will solve the dual problem. And then if there is not a saddle point of this Lagrangian, we will have to do some things, but it will give us already a good price signal solving this problem. The dual function is concave, is non-smooth, and not explicitly available, and this is important too. So here I just copied our function, and if we look at the term related to the variables, the thermal variables, you see that the function is the minimum of functions that are affine of x, as a function of x. So it is this drawing here, all those lines, we take the minimum, and then the dual function theta is this blue function. And what is, similarly for the hydro term, the theta h, and what is important here are two things. First, we don't know it, we don't have it explicitly in an open form, right? For every given x, we have to solve an optimization problem, where here there are all the complicated constraints related to how we produce power of this type. So for each x, we know the value, but we don't know, of course, that it has this form. Well, we know that it is piecewise affine, but that's all, but not exactly where. And another thing is that we want to maximize it, and usually the maximum is at the kink, is at the point where of non-differentiability, where two or more lines coincide. And when two or more lines coincide, that means that more than one G here achieves the minimum, because one and one, this one corresponds to different Gs. Okay. Why separability is important? It's relevant because, like this, as I said, we are able to put all the detail in the operation of the and the way of generating energy for each technology, and then computations for evaluating the dual function can be done in parallel, separated for each technology. So this is also important. Okay, so this part. What are our messages? Marginal prices are Lagrange multipliers. For large power systems, it is useful to pass through the dual to solve the problem. And we get, in that way, marginal prices by solving this dual problem. So if we are able to maximize this concave non-smooth function fast, and accurately, that would be ideal. So fast would be, we would like to do Newton. But how can we do Newton? A Newton method. We would like to apply Newton method for a function that is non-smooth. From the beginning, all our drawings were nicely and smooth. So we don't even have C1, our function, because we have breaks. It's in the points where more than one affine piece achieves the minimum. They are not even of C1. So how do we do? The answer is related to our third question. So the third question is answer is provided by the works of Jean-Jacques Moreau. Jean-Jacques Moreau was a French past 5 years ago who was working in mechanics. He described himself as a mechanicist who does mathematics, something like this. So always very broad and here for some sweeping processes introduced the Moreau envelope of the function. A function, suppose now we have a convex function, so we are turning upside down our concave dual function. It is convex now. So we have a lower semi-continuous convex function here, and for each point we compute the result of this optimization problem that depends on a parameter that is called the prox parameter, and this gives us something that depends on x, right? This is a function that is a smoothing of the original function f, and the Moreau envelope is pretty smooth. It's C11 without much on the without any assumption on the function f. Okay, and another observation is that since this is a quadratic term here, there is a unique minimizer. It's a unconstrained problem. There is a unique minimizer. And the minimizer of this optimization problem is the proximal point. When considered as a function of x, is a proximal point mapping. Okay, so here we have the simplest non-smooth function. The absolute value function is a maximum of plus x and minus x. And then in red there is the Moreau envelope of this function. So as I said, the unique minimizer is the proximal point, and when we consider it as a function of x, it's a mapping. And as you see here in the drawing, the fact that minimizing the green function and minimizing the red function is equivalent, it's a theorem. It's the same then to minimize the original function than to minimize its Moreau envelope. Okay, and minimizing the Moreau envelope unconstrained on x, you have to compute it's the same than zeroing the gradient. Here is the expression of the gradient of the envelopes is this term mu times the point minus its prox. So zeroing the gradient means this equal to 0, and that means that x is equal to its prox. It's equivalent then to minimize this function, the original function, minimizing the Moreau envelope, or finding the fixed point of the proximal point operator. Okay, of course, to minimize this function, we have to, it's a lot of work, but it's smooth. And another thing is that, well, this gradient is Lipschitzian. So it is C11, the function, because the Jacobian is Lipschitzian. The Jacobian, no, the proximal point is Lipschitzian. So as I said, the proximal point mapping, finding the fixed point of the proximal point mapping is equivalent to minimizing this function. This is a result by Martinet. And then what do we do when we have a fixed point problem? We apply the Picard's iteration and see what is it the sequence that we generate. So we take the proximal point of one iterate, we take the next, and so on. So this is a method. In this case, it converges, but it is known that it is rather slow. And to understand why it is slow, we rewrite here. You see, I did plus minus x and divided mu by mu, and we got here. And then here, if you don't remember, I remind you, this is the gradient of the Moreau envelope. So in fact, what the method, Picard's iteration is doing, and this is a proximal point also method, it's doing a gradient step to minimize the Moreau envelope. And this is why it's slow, because it's a first order method. You saw what happens with first order methods. So this is the interpretation of this envelope, of this method. So can we do something to improve it and try to make it look more like a Newtonian method? Then, if you remember here, the Newton method here had the inverse Hessian, right? And it was fast. Okay, so for that we can, instead of the prox parameter mu, we will use a positive definite matrix that induces a metric, and then we'll have the quadratic term induced by this metric. And then we have all the same results than before. We have a proximal point. The proximal point is Lipschitzian. The gradient of the Moreau envelope satisfies this property, and it's equivalent to minimize one function is regularization or finding the fixed point of the proximal point operator. Why are we doing that? Is because now we perceive better what is the role of this metric. Because if we do here the same game than before, except that instead mu divided by mu is the inverse matrix plus its inverse, we see that the metric, in fact, is something to be fast. It should approximate the second order of the Moreau envelope. This is the metric that we should be using to have fast convergence. So we were very happy when we found that. But we said, oh, wait a minute, the regularization is C11. We need a little bit more. We need C2 in the solution and X star. Can we ask that this Hessian exists? Well, the answer was negative. The answer was negative, and we were very sad for a while, because what we knew is the line on top is the result from Moreau, that for a convex and lower semi-continuous function, we have a regularization that is pretty regular, but if we ask a little bit more, that is C2, I drop here all the mu or m, just F is the Moreau envelope. Then if we ask that is C2, then the original function has to be C2 everywhere. And this is, well, what is the meaning and what is the utility of applying a regularization to something that is already regular? Just do a Newton method to the original function, but we don't have a function that is regular, that is smooth. So, well, we were breaking our head for a while, and it was a little depressing. The good thing is that I already had my PhD, so it was not finishing my career as a researcher, it was afterwards. So, until we started observing a little bit what happens when the Hessian, for some prototypical examples, when the Hessian of the Moreau envelope exists. Well, it depends on the Jacobian of the proximal point operator, right? Because here what depends on x is the proximal point operator. And when the Jacobian exists of this proximal point operator, it was not defined everywhere, lying everywhere. It was in some subspace. And then we remember quasi-Newton. We don't need things to happen good things to happen in the whole space. We need to work in subspaces, and that was the key. The key was to decompose the subspace. At that point, we realized that non-smoothness doesn't arise arbitrarily in the universe. And there are many, many functions where non-smoothness appears in a structural way, with certain structure. As I said, the absolute value function, that is the maximum of two functions, and then the non-smoothness is where the two plus x and minus x coincide. So this type of structure, where whether if it is a function defined by the maximum or an eigenvalue, for an eigenvalue, if you want to find, for some stability reason, we want to minimize the maximum eigenvalue, then associated to this eigenvalue there are eigenvectors, and if there is more than one eigenvector, there we have non-differentiability. Okay, and this is a structure that is very specific and that exhibits some kind of smoothness in this non-smooth setting. So how is it that we did? So we realized that we don't have to look for second order everywhere. We just need to find this subspace of smoothness U where the function looks smooth. So we define the composition of the space that when looking at the function from the V subspace, the function looks non-smooth, is sharp, all the non-smoothness is concentrated there. But suppose that this is a book that is walking like this in a parabol. If we are an ant walking along this valley, the ant will not realize that it is non-smooth, right? It will only see the valley, right? And this is the subspace on the right, where the function looks smooth. The subspace definition depends on the subdifferential of the function at the optimum. Okay, so to make the ideas more clear, suppose that we have this very simple function where we have the square root of a quadratic form, where here a is semi-definite and a quadratic term positive definite. Because of this quadratic term, the minimum is at 0, but when we take the derivatives, the square root goes to the denominator, and the function fails to be differentiable where in the null space of A. There is the non-differentiability. But, wait a minute, let's go back. But if we take points that are in the null space of A, the first term vanishes, and then the function looks smooth. Okay? This is the idea, this is the decomposition. If we manage to identify this subspace where there is a non-differentiability, the function will look smooth otherwise. And if it looks smooth, we can use a Newton method in that subspace. So that's the idea. Here again are the v and u views of this function, depending on which subspace we are looking at it. And these are perpendicular on subspaces, orthogonal and complementary subspaces, so they define the whole space. And then just look here, and I will. This is a function of this type with structure. What we are looking for is this. Is we are trying to find this valley of smoothness, and if we are able to identify this valley here, we can do a Newton method. Okay, so how do we do it? So we develop some theory, and we call it the U-Lagrangian. I will not give you the formulas. I will give you just the main concepts behind it. It's a nice variation analysis theory, first in convex case and then in non-convex. So what is this valley? This is where, if we walk there, we will not realize that we are in the break of the derivative. And this valley, this black line here, is characterized as a manifold, a concept from differential geometry, is a smooth manifold. For many functions with not much properties, like reasonable properties, there is this activity manifold. And what is more important, we can parameterize all the elements in this manifold all in the U subspace. It will have the V component, but the V component will depend on U. And the points on in this manifold have a small V component, and this makes it that if we do a Newton step in the U, in this manifold, then the speed of convergence of the whole method will be driven by the speed of convergence of the method we use in the U subspace, which is Newton, so it will be fast. And how do we find elements in this manifold? Here comes the proximal point. If we compute the proximal point, we will locally then find elements in the black line. So it is a combination of two ideas. And this U-Lagrangian, what it gives is this black line, this the elements, the functional elements here along the manifold, and it is smooth. When it has second order, which is also reasonable in many cases, we can use a Newton method on the U-Lagrangian and get fast convergence. This is the idea of this all this combination of things. And as I said, this type of situations where we can use and identify this activity manifold appears often in optimization, when a function is defined as a maximum of other functions, whether the maximum is a supremum or a maximum, and this, as it is the case of eigenvalue, for example, the maximum eigenvalue, or maximum function that is a maximum, or the dual function that we were considering for electricity. So just graphically how this method does, it alternates a V step and a U step. The V step is just computing the proximal point that brings us here. This blue line is I turn upside down the black smooth trajectory. It brings us here. And then once we are in our smooth manifold, we can compute the U-Lagrangian and make a Newton move, but along this U-Lagrangian. So we do this predictor step, then we correct with the proximal point, and so on. And this is a method that converges fast. And to show you, I have just a couple more of slides to show you. I'm sorry, I don't know why I couldn't make it darker, because this is the one that I'm interested into. But well, anyway, so I will talk to you about this. This is it is a function that is typical in non-smooth optimization for testing. It's the maximum of 5 quadratic functions in R10. That at the optimum there are 4 of them that are active. All of them coincide. So it makes very difficult the calculations, but this means that this manifold of smoothness has dimension 7. And the V subspace dimension 10. So if we use in red here, so on the ordinates we have the error, so we want to go to 0. And here on the abscissas the number of iterations. On red is a first order method in non-smooth optimization that is rather good, but it's bundle, and it's a bundle method, but it's first order, so it's low where you don't get much more than 5 digits. And then on blue here, it's a Newton type method of VU, a VU but Newton. Since this is a problem where we know all the information, we can use the Newton approach. We can compute approximations for the Hessian. Here is a Newton, where you can see the superlinear, the more than superlinear convergence, and here the invisible one is the quasi-Newton that also gives us quite a lot of digits in a reasonable number of iterations. Now, if you are somebody who likes nonlinear programming, you are a nonlinear programmer and are used to BFGS or any quasi-Newton method, you could say, okay, I will ignore that the function is non-smooth and I will just apply my method as I know it, because I know all the tricks for line searches so that it doesn't get trapped in kinks and so on. What happens? This happens. Those are, I had to pull it from another drawing, so that's why it's a little strange, but this is the iterates of a BFGS method for smooth functions will stop here and will not be able to get you. It works well, and it's interesting because it's very well done. It's by Michael Overton, this implementation, who knows quite a lot. It works better in terms of course, much more iterations and calculations, but in terms of accuracy than the bundle method, but well, it has a limit and it cannot go further. Okay, so now I'm getting to the end of my talk. I thought it was suitable to remember what is an archetype. It's a typical example of something, or the original model of something from which others are copied. And I think that in that sense, the 3 characters that I presented are archetypes, and that, well, they are the original models and that we would all like to copy them. So Newton, Lagrange, and Moreau. And what I like about the work of these very important mathematical characters, I don't know, characters sounds a little bit diminishing, but persons, I don't know, celebrities, is that they were transversal. They were promoting, or well, probably they were not even worrying about this type of math, or this type of math is math that is exciting, that drives me to want to research more and more and to do better math later on. Okay, so then this is the end of my talk. Thank you.
Thank you, Claudia. We have time for 1 or 2 questions or remarks. Maybe I have a question. The V and the U, what's the origin of those 2 letters?
Sharp and smooth. It was UV in the beginning, and then we realized that VU and VU, it was better, and we changed the order.
Yes.
How accurate do you have to get back onto the subspace so that you can actually take a really good U step?
It depends on how easy it is to compute the props. There are now, for all those methods that assume that the proximal point is easy to compute, then it can be, you can allow yourself to do it. But we are trying to do for lasso and all these type of problems. We don't have enough experience yet in that one. In this one, we were in the non-smooth for the dual function, where you don't have the information of the function. We were doing always 1V and 1U steps, so 2 quadratic programs per iteration.
As a foreigner, I have a question. So what is the difference between archetype and paradigm? Because it seems the definitions are close.
Maybe one is Greek and the other one is not.
Okay.
No?
But you know that there exists this monument of paradigm in London. It's close to this Pancras station. Monument called Paradigm, very beautiful one, 14 meters, yeah. So maybe now
go.
asked to produce an archetype.
Yes.
Okay, well, we have some drinks outside, I think, that everyone can enjoy and meet our speaker and talk to her afterwards. But I'd just like to thank you once again for a very well prepared and interesting talk. Thank you very much.
Thank you.